Bio-Rad has produced a new cutting-edge QC performance assessment and design technology. This video uses simulations of a glucose assay to illustrate and explain some of the key concepts that are involved in our computations. Let's begin by orientating ourselves. Glucose results are represented on the vertical axis, and time is represented on the horizontal axis. Let's assume that our glucose method has a coefficient of variation of 2.5%, and that we've established an allowable total error criterion, our quality requirement, of plus or minus 10%. Now let's imagine that we are in the laboratory doing routine testing. We expect results to be evaluated over time. Here we can see the distribution of results. In this case, they range from about 50 to 300. We recognize that the results we are recording are not perfect, and that each result has some degree of uncertainty associated with it. In reality, each of the dots would be better depicted by a vertical line that represents uncertainty in the measurement result. In this particular case, where we are assuming a CV of 2.5%, large results like the glucoses that are around 250 have more uncertainty associated with them than the smaller results that are closer to 50. Here we see the simulated measurement errors for the results displayed above. These were randomly generated, assuming a coefficient of variation of 2.5%. The lower right panel is a histogram of the measurement errors. Now let's continue to measure results. Again, here we see the results as well as the distribution. Note the horizontal dashed lines at plus or minus 10. These are the limits set by the quality requirement. Likewise, the vertical lines in the right panel serve the same purpose. We can compute and predict the likelihood of producing a result that fails to meet the quality requirement by the number of observed measurement errors that exceed plus or minus 10%. If you look at the lower right panel, there are no results that exceed the limits. This is because we have a TEA of plus or minus 10%, but a CV of 2.5%. So the chance of getting a result with a measurement error as high as 10% is very low. In fact, in this case, percent question mark representing the percent unreliable is 0 when rounded to the nearest 1/10%. Let's look at a different case. Before, we used the CLIA recommendation for our TEA, 10%. Now let's use 6.9%, a specification used in Belgium. We'll only change that parameter and then rerun the simulation. Notice that the distribution of results in the upper and lower panels are unchanged. But the locations of the dashed lines have changed. They are no longer at plus or minus 10%. They're now at plus or minus 6.9%. Also notice that we now have a result with measurement error that exceeds 6.9%. It's denoted in red. It doesn't exceed 10%, so it wouldn't have been red earlier. Let's make another observation about the result that isn't meeting the quality requirement. There is nothing about this result that would give a laboratorian a clue that it contained an unacceptable amount of measurement error. If we continue to measure results, we see a few that are failing to meet the quality requirement. The histogram is the same as it was before, but now we see that 0.6% or 6 out of 1,000 fails to meet the quality requirement. Looking at data in this manner turns out to be an interesting way to appreciate the likelihood of producing results that fail to meet the quality requirements.